In this video, we consider the moving average model of order Q, the MAQ model. The MAQ model for the time series yt is given by a constant term plus epsilon t plus alpha 1 epsilon t minus 1, and then we have up until alpha q epsilon t minus q. And this is for t equal 1, 2, all the way up to capital T, which is our sample size. We make the assumption that epsilon t is IID, it is independent, and it has the same identical distribution. It has a mean of 0 and a variance of sigma squared. We refer to this as a white noise process, and it is stationary by construction. For the process yt, note that if we are initializing y at t equal to 1, we need to know the value of the past shocks. So in addition to t equal 1 to t and the assumption about the epsilons, we need to make the assumption that the values of epsilon 0, epsilon minus 1, all the way up or down to epsilon minus q plus 1, that they are given, meaning that we condition on them, we treat them as observed, and usually we simply set these values to 0. We can study the properties of the process directly from the equation we have here, and what we want to show is that this process is indeed stationary for all parameter values for alpha. Note that this is just a sum of stationary terms, so yt is stationary by itself. The first thing we want to show is the expected value of yt. Now we simply plug in the expected value of the constant term plus epsilon t plus alpha 1 epsilon t minus 1 all the way up to alpha q epsilon t minus q, and then we take the expected value of each of the individual terms, and that just gives us the constant term. Note that the assumptions we made about epsilon t implies that the expected value of epsilon t is equal to 0. That's for all t. And also note that because it's independent over time, the covariances, or the expected value here of epsilon t minus h, is equal to 0, and that holds for all h not equal to 0. So this was the expected value that is simply given by the constant term mu. It is constant and it does not depend on t. Second, we can look at the variance of yt. That is the expected value of yt minus its unconditional mean, which we just found to be equal to the constant term. Here again, we simply plug in. So this is the expected value of, and now we subtract the constant. So we get epsilon t alpha 1 epsilon t minus 1 plus all the way to alpha q epsilon t minus q, and then we square it. Note that when we square it, we get each of the individual terms squared, and then we get a lot of cross products, and all the cross products are 0. So we can simply write this as the expected value of epsilon t squared plus we get alpha 1 squared, the expected value of epsilon t minus 1 squared, plus all the way to alpha q squared, the expected value of epsilon t minus q squared. And then we get all these covariance terms which are equal to 0. Note that the expected value of epsilon t squared is just given by the constant, by sigma squared, which is constant over time, which implies that we can write the variance as 1 plus alpha 1 squared plus all the way up to alpha q squared multiplied by sigma squared. Note that this is constant, does not depend on t, it only depends on the moving average parameters alpha and then the variance of the epsilon t. So this was equal to gamma 0, the variance. Next we want to study gamma 1, which is the covariance between yt and yt minus 1. We simply plug in again, so we get epsilon t alpha 1 epsilon t minus 1 plus all the way to alpha q epsilon t minus q, and then we have to do the same for yt minus 1. So note that what we get here is epsilon t minus 1 plus alpha 1 epsilon t minus 2 plus all the way to alpha q epsilon t minus 1 minus q. We simply multiply these together, and again we note that all the cross products are equal to 0 because of the independence over time, and all we are left with is the common terms. We have epsilon t minus 1 here and here, and then in the end we have all the way to epsilon t minus q, and note that over here we have an epsilon t minus 1 minus q, which we only have in the second part and not in the first. So we have two terms which cancel out, so to speak, and all we are left with is the terms from epsilon t minus 1 to epsilon t minus q squared. That implies that if we multiply this together and we rearrange, we get a value for the first covariance, the first autocovariance, which is equal to alpha 1 plus alpha 2 alpha 1 plus alpha 3 alpha 2 plus all the way up to alpha q minus 1 multiplied by sigma squared. Again, this is constant over time. It does not depend on t. Now we could do the same for the second autocovariance, or we could simply go directly to gamma q and note that this is simply equal to alpha q sigma squared. If we have alpha q plus h, these are 0 for all h positive. We have now shown that the expected value, the unconditional mean, the unconditional variance, and all the covariances, all the autocovariances are constant over time. They do not depend on t. So we have shown that the MA1 process here is stationary by construction. It is stationary for all values of the alphas, because the yt here is simply a sum of white noise processes which are stationary by construction, so yt itself is stationary. Finally, we could look at the autocorrelation function. So rho k is defined as the kth autocovariance divided by the variance. And note that we could rewrite the kth autocovariance as alpha k plus 1 alpha 1 plus alpha k plus 2 alpha 2 all the way up to alpha q minus k, and then we have a sigma square out here which cancels out. So in the denominator we get the variance which we had up here, so we get 1 plus alpha 1 square plus all the way up to alpha q square, and note that the sigma square we have both here and here, they cancel out. So this is for all k less than or equal to q. At the same time we get that rho k is equal to 0 for k greater than q. We have an autocorrelation function which is not 0 up until the qth autocorrelation, and then it becomes 0. So we have a memory of exactly q periods. Finally, let's just very briefly consider the MA infinite model. So this is a moving average model with an infinite amount of lags. And note that this is stationary if the sum from j equals 0 to infinity of each of these moving average parameters squared is less than infinity. So this means that the sum of the moving average coefficients convergence, it's an infinite sum, and it has a limit, a finite limit. If that is fulfilled, the infinite moving average model will indeed be stationary as well. That's all for now. Thanks for watching.